one cylinder. Okay, I don't know, maybe one mission concept. I'm gonna find more 7 nation. अच्छा ना meet.google.com है डाउनलोड से जाओ तो खुले छी Hello everyone, welcome to week 8 of problem solving session for split spectrum. Today we will be doing tracking of DSSS and FHSS. The topic today is the tracking of DSSS and FHSS. So first we will go through DS3 tracking. The theory of DS3 tracking. Again, there is not much to do in the way of problems here. So we will be just doing a brief revision of whatever has been taught till today in this week, and we will just do a brief revision recap of the entire week. From the next week, I hope there will be assignments which will have problems and we can solve those problems, but now it's mostly theory as we will be describing machinations of DS3 tracking and FHSS tracking. So the first thing that we have to note is in DS3, all the codes DS3, all the codes generated at the transmitter and the receiver, the PN sequence codes, should exactly match. If there is even the slightest mismatch of codes generated from DS3, from DS3 transmitter and receiver, there will be even one bit synchronization error will cascade into a proper error. So this is accomplished by generating a local replica of the PN code in the receiver and then synchronizing this local PN signal to the one which is superimposed on the incoming waveform. So this local replica, we have to generate a local replica of the PN code in the receiver, and that is where the synchronization comes in. The synchronization has to be picture perfect, or else even one bit synchronization error will lead to complete mismatch in the detection. So that is a key disadvantage of DS3. So we have to make sure that the local replica of the PN sequence generated is synchronized properly with the actual PN sequence transmitted. To ensure that, we have to do what is known as PN sequence tracking. So the process of synchronizing the local and received PN signals is accomplished in two stages. One is the PN acquisition, where we decide what is the PN sequence that is being transmitted, and another is PN tracking, in which we constantly update any changes in the incoming PN sequence at the local replica of the receiver. So PN acquisition is initially, so the PN acquisition is the broad agreement of what PN sequence was originally sent, whereas PN tracking is the finer bit level synchronization that we have to continuously carry out. So initially a coarse alignment of the two PN signals is produced, two PN signal elements, the one that is at the transmitter and the one that is replicated at the receiver. Initially coarse alignment of the two PN signals is produced within a small fraction, typically residual relative time offset. The process of bringing two codes into coarse alignment is referred to as PN acquisition. PN tracking, once the incoming PN code has been acquired, then we have to do a fine tuning of sort, that is a fine synchronization. So a fine synchronization system takes over and continuously maintains the best possible waveform alignment by means of a closed loop operation. So it basically tries to latch onto the incoming PN sequence and tries to be in lockstep with the incoming PN sequence as much as possible. So once the incoming PN code has been acquired, a fine synchronization means of so we run a closed loop operation to latch onto whatever is being transmitted. So the tracking part, in the previous week we have done the acquisition part. In this week we will be doing the tracking part. So in tracking DS3 signal means the process of keeping the receiver's local generated code sequence in lockstep with the incoming code sequence. This is necessary for the receiver to correctly decorrelate the signal to extract the data. It also spreads any interfering signal, although proper synchronization it's not necessary to accomplish that. So it also spreads any interfering signal. So first is the primary sequence. Primary task is to keep the locally generated code in lockstep, and the secondary task is to second uh, and the secondary task is to spread any interfering signal. While there are numerous techniques for implementing DS3 tracking, most are based on delay locked loop. So the method used for DS3 tracking is delay locked loop. The delay locked loop relies on theoretical triangulation of the correlation function of n sequences. Okay, so let's see a delay locked loop. So a delay locked loop basically has D flip-flops, XOR gates, accumulators, adders, and clocks. So and a code generator which generates the PN sequence as and when required. So yeah, the the locally generated code sequence is sent to a three-stage shift register. The last stage, which represents a delay in of three chips in the sequence, is the late code. Uh, the three stage the locally generated sequence is stayed into a three states. So here you can see there are three states. Three state shift register. The last stage, which represents the delay of three chips in the sequence, is the late code. The code sequence from the middle stage is used to decorrelate the incoming signal, and the sequence from the first stage is the early code. So this is the early code, this is the actual code, and this is the late code. So the incoming code sequence is modulo 2 added to the early PN local PN sequence in the upper path. So modulo 2 addition means XOR. So whatever is incoming, that is XORed with early here, and here it is XORed with late. So one time it is XORed with early, one time it is XORed with late. Okay. If they are synchronized, then the correlation function shown at the top of figure 1b is generated by the early correlator. So the early correlator will generate the particular triangular signal, and similarly if the late is in lockstep, if the correlation signal in 1b is, so the incoming code sequence is modulo 2 added to the late local sequence in the late correlator. The difference in the two correlation function when in sync is shown at the figure 1. So basically when in sync, the early late, there will be a difference, and that difference is this. Okay, the difference when in sync is shown that and there is a balance point that always occurs at fixed point in time after the chip starts. So if they are in sync, then you will have two perfect triangles in the early and late correlator like this. And when you subtract them, you will always get a null point. That particular null point is called the in sync point here. So the incoming code sequence is modulo 2 added to the another example of a correlator that would merge. Huh. If this point occurs at some other time, depending on which side of the in-sync point it occurs, it indicates that the clock should be. Now, if this in-sync point exactly happens in the middle, then that is fine. But if it is offset from the middle, that means that much amount of the delay adjustment must be done. So yeah, that if this so the occurs okay, and there is a balance point in sync point that always occurs at the middle of the chip. If it occurs at some other time, depending on which side of the in sync point it occurs, it indicates that the clock should be delayed or advanced. So another one is the parallel correlator. Another example of a correlator that would work in this figure 2 shows another example of a correlator that would work in this scenario. Here you have a receipt sequence which goes through a shift register, and you sequentially add the particular elements of the reference sequence and the receive sequence, and you do a modulo 2 addition, that is OR. You XOR the receive sequence and reference sequence. So whenever there is a difference, that particular one will be 1. So okay, so basically each bit of the receive sequence, each state, uh, now basically in this one we are adding PN sequence, that is received with a reference sequence that we think is the reference sequence, and then basically we do a solve of bit by bit. Now if any of the bit, uh, if any of the bit is zoring with any other bit, then if they are equal it will get 0, if they're not then it will give 1. So if we get anything non-zero in this output, means there is one or more than one ones here, that means one or more than one bits are not matching. So that is a simple parallel correlator, but this does not give you a diagnostic. This only gives you that something is wrong, but it does not give you where it is going wrong, whether it should be advanced or it should be delayed, nothing like that. Whereas this is a much more sophisticated uh, DLL for DS3 code tracking, as this will give you whether the clock should be advanced or delayed based on the in sync point. So whether the code generator will should be advanced or delayed based on the in sync point. If this in sync point is exactly in the middle, means everything is perfectly in sync. Uh, So here this one is much more sophisticated, and this one is a very simplistic way of doing DS3 synchronization. Now we will come to FHSS synchronization. that is frequency hopping spectrum synchronization. The basic principles are similar to DS3. However, the details are different. How? Because uh, here the frequency is changing according to the incoming code. So the synchronization process here is even more critical, as the frequency with which it will be transmitted depends on the frequency with which it will be transmitted depends on the PN sequence code. So frequency is very fundamental to the communication process. So if a jammer can try to attack the synchronization process, so if it fails, the if HSS network fails to synchronize, it cannot communicate at all. So the environment considered here consists of push to talk networks, where consists of push to talk networks in where for which there may be extended periods of no communication. Push to talk means whenever someone has some message, they will communicate. Otherwise, the message will stay silent. Otherwise, the signal will stay silent. Okay. Now, with that, on the environment in this time the clocks in transmitter and receiver may have drifted apart. So when they are not communicating. In that time, the clocks of the transmitter and receiver may have some kind of a mismatch between them, and this will create an out of sync issue for the frequency hopping spectrum. Thus, before every FHSS Thus, before every FHSS transmission, the transmitter and receiver must be synchronized. Okay. Although in general a two-dimensional search is required over both frequency and code, that is, what frequency you are transmitting. So here in FHSS, basically you have a frequency range, and within that frequency range, what particular frequency you are transmitting, that depends on the code. So you have to first know what is the frequency range. What is the frequency range of the transmitter, you have to know, and then you have to know the code to know the exact frequency at which it is transmitted. So knowing the frequency range will give you a course adjustment, while knowing the exact code will, after knowing the frequency range, if you know the exact code, you will get a fine adjustment, you will know the exact frequency. So you have to have two means two informations. So in many cases of practical interest, such as ground deployed PTT communication network, this is a safe assumption. It may not be a safe assumption for high velocity aircraft communication. So here the frequency search will be ignored, because basically what is understood is that you may choose some frequency, random frequency, in the range of the what is set. So if your transmitter is transmitting between 5 and 10 megahertz, you might choose anything between 5 and 10 megahertz. But it is understood that because the dynamic range is 5 to 10 megahertz, so you won't simply give 1 gigahertz or something. You simply won't get that. You will get something between 5 to 10 megahertz. So you do not need to do a frequency search. But in many cases, a frequency search is necessary, such as an example might be that high velocity aircraft communication. Now, with this technique, a leader is transmitted prior to sending any data from transmitter and to receiver. So, the leader is comprised of several passes through hop set with known data sequence attached. So, basically, like a pilot you are sending, and that pilot will hop through multiple frequencies and will check whether it is locking onto the frequency or not. When In general, okay, in general, if the, so basically there will be a pilot, and that pilot will hop through many frequencies, and it will see where it locks. If it locks in a particular frequency, then you can be certain about the frequency range. That is the leader or the pilot. And if the synchronization search fails on the first pass through the search phase, additional passes can be attempted. Okay, so basically we will hop through multiple frequencies till we finally arrive at the frequency. The number of hops in the synchronization sequence here is denoted by h. Okay, so the received signal during kth hopping interval of the synchronized process can be decided as fk. Fk is the hop particular kth hop frequency, theta k is the carrier phase, and r is the average power. The probability of detection of the signal is given by Pd equal to P z greater than gamma th, where gamma th is the threshold probability, the threshold SNR. Okay, so basically the threshold at which we will say make a decision one way or another. So the probability of detection is given by this. From there, basically you get the probability of missing a particular hop, and from there uh, you will from there the probability of miss is given by the complementary hop. So basically, how what is the probability that a particular search will give you a correct result or not? Yeah, so the probability of detection is given by this. Here we will the probability of miss is given by 1 minus of that. This analysis includes communication. Now, what is the environmental assumption for this analysis? That the communication is a Rician feeding channel with potential interfering emitters, including tone jammers, impinging on the receiver. So we incorporate all that to get the particular hop frequency, and then we have the particular jammer, and here R is like the you have noise. So yeah, so here we have split it into the the signal into two parts. One is the LOS part and another is the non-line of sight part. So the direct component and the reflection component. The factor AI accounts for the factor AI, this one accounts for the 1 minute. The factor the CJ factor account for the random fluctuation in the reflected component. So this is basically the reflected path loss, and this is the direct path loss. Okay, so with this we will get the particular the received signal in this hopping environment. Now, the number of channels available to FHSS system is denoted by F, and it is assumed that each of these contain interfering tones, all of which have power equal to the intended signal, independent of each other. That is, basically you have F number of tones. So out of that, maybe one is the particular user is using, but there are F number of total tones available. So the rest will of course be used by other, the rest will be used by yeah, the rest will be used by the other users, because that is the point of this FHSS, that we will all hops will not be used by one system at once, so we can assign the other hops to other systems, and together we can multiplex a lot of users. So if you consider from one user's point of view, the other users are interferers, So each of these contain interfering tones. That is, those are the incorrect hops. If you are locking onto a particular hop for a particular user, the other hops are interfering tones. So each of these contain interfering tones, all of which have power equal to that of intended signal. So basically the power is equally distributed among all users, independent of each other with uniform random phases. While these are gross assumptions for co-channel interference, they do facilitate an approximate analysis of the effects of interfering signals. Okay, and the probability that k channels have an interference. Okay, so a particular channel out of 8 channels, what is the probability that k channels will have interfering tone? That is basically every channel is either interfering or non-interfering. So you are choosing. So of course this will be a binomial distribution. So here you can see it is a binomial distribution. H choose k, p to the power p hop to the power k, and 1 minus p hop to the power h minus k, where p hop is the probability that it is occupied with one interfering channel. Okay, that particular channel is an interfering channel. The probability of declaring synchronization on a single pass when in fact synchronization is not present. So basically synchronization's probability is this, and when in fact synchronization is not present, so this will be given by the probability of this detection. So you have detected, but it is actually an interfering tone. This is the probability of having an interfering tone, and this is the probability of synchronization. This is the probability of synchronization, and this is the probability of having an interfering tone. So what is false alarm? False alarm is when you have synchronized, but it acts with a particular hop, but that hop actually contains interfering tone. So you have synchronized with an interfering tone. So you have not synchronized with the intended tone, but you are giving an alarm that you have synchronized with the intended tone. So you are giving a false alarm. So this is the probability of false alarm. Now the probability of false alarm, as you might know, is a very important metric in designing this kind of receivers. The probability of false alarm is usually specified to be a particular value, and all other design parameters are chosen around it, because a false alarm is very concerning for a system and it should be avoided to the maximum extent. That's why we will say that we cannot tolerate a false alarm probability more than 10 to the power minus 5. But we cannot tolerate a probability more than 10 to the probability of false alarm more than 10 to the power minus 5. But what we will do is we will design the system accordingly. We will make compromise on other parameters, but if the design is said that PFA is 10 to the power minus 5 less than 10 to the power minus 5, we have to make it. So that is why PFA formulation here is very important. We can work out the parameter values from this equation given a particular PFA. Okay. Now Pn is the total noise power. So the total noise power is given by this sigma square, which is the AWGN, and another is the Br. Why does this Br come now? Because of interference. Okay. So it is basically not SNR but actually SINR. Okay. Now the probability of not achieving synchronization when the sync sequence is present. So now we are doing a probability of misdetection. That is probability of false alarm, probability of misdetection. These are the two parts of the confusion matrix. So I think you are familiar with confusion matrix. If not, I will still draw once. So yeah, oh, it is drawn already. So see here, there are, this is the confusion matrix. So if there is no synchronize, here it will be not be signal but synchronization sequence. that is the PN sequence, correct PN sequence. Synchronization sequence is basically the correct PN sequence. So if you achieve synchronization, so let's reformulate the confusion matrix accordingly. So on one axis you have achieved synchronization of FHSS. So whether you have achieved synchronization or not, that is one question you are asking. And the second one is sync sequence, correct? That is, have you arrived at the correct synchronization sequence? Have you predicted the correct sequence, correct hop? So that are the two questions. Now if you say you have achieved synchronization, yes, but the sync code is not correct, that means you have done something which you shouldn't have done. So you are getting basically false alarm. You are giving a false alarm. You are shouting sync achieved, but you should not have got sync. Now, the opposite of this is when you haven't achieved sync, but you have predicted the correct sequence, but you still fail to say that you have achieved synchronization. In your unbeknownst to you, you have predicted the correct sequence, but then with your own calculations you said, because your calculations didn't give you a proper threshold crossing, you say that your gamma was not crossed, so you say you haven't achieved synchronization. So basically you missed a chance. So this is the probability of misdetection. So this is also known as the false positive. This is also known as, in general terms, it is known as false positive. This is true negative. This is true positive. And this is false negative. And these two are desired, right? So these are P1 and P2. Now any event will of course will have, you can either do P1 or P2 or PFA or PMD. You have to do one of those four. So these will of course equal 1, because you have only 4 options. Now let's go. Okay, now FHSS, this is the missynchronization or misdetection. So these are the probabilities. Now we come to a new method of FHSS synchronization, which is the matched filter. So matched filter means whatever signal you are getting, whatever signal is incoming, you try to make a filter that will give you a matched response to that. Matched response means your filter response should be a time delayed version of your signal. So you say that your filter is matched to a particular signal when h tau, the particular signal, is nothing but x t minus tau. The t is a particular delay. So this is the match condition. So a filter is matched to a signal if it satisfies this property. So the first technique of FHSS code synchronization employs a matched filter. This is the matched filter. The detector is normally implemented at 8 successive frequencies. So you have filter bank. Each filter in that filter bank is designed for a particular hop. It's a particular hop. So each of them, like f1 is one hop, f2 is one hop, fh is the final hop. So there are multiple hops, right? H total, capital H number of hops, so capital H number of frequencies. So all these capital H number of frequencies, each one will have a particular filter. So you basically split this incoming signal into I and Q, then filter them, then accumulate them and sum them. Basically you are doing a correlation. So you are doing you correlate them, and you correlate this one, and you correlate this one, and finally you will get whichever is like matched filter. You will get the particular response from there. The others will be not matched, so you will get a different kind of response from there. That is the principle. So basically, if you have to now, what kind of different, basically you have to figure out a particular threshold, and you will see that the one frequency hop in which it has synchronized, the one frequency hop in which it has synchronized will give you that one the one figure will give you a correlation value that is above a certain threshold, whereas others will give you below the certain threshold. So that is the theory of matched filter. Okay, so with this, the method of synchronization is faster than serial search technique, but the probability of false lock is much higher. So here basically you are depending on a what particular threshold, and depending on how well you have got that threshold down, you may or may not have the proper detection. So you might have a false alarm. So even if there is no correlation, it, you might get a threshold that is crossed. The matched filter method, since several parallel channels are working at the same time, will have much more components. Of course, there is a lot of components. You can see there are filters are plenty here. So if there are H hops, so you need 2H LPFs, and then H number of BPFs. So 3H number of filters. Along with that, you will need 1, 2, 3, 4 4H number of multipliers, and then you will need H number of accumulators, H 2H number of square law devices, H number of delays. So a huge number of components will be involved. Okay, the performance of the matched filter code acquisition system with H equal to 5 interfering signals. So if there are 5 interfering signals, you can see that this is the probability of missed code synchronization. So as you increase the VER, your probability of missing synchronization is, as you increase the SNR, your probability of missing synchronization reduces. Further, if you change the total number of available hops, because in this one you have uh, 5 interfering signals, here you have 10, then you have 20, then 30. So yeah, the performance of the with H for this there were no jammers. The average time to take is for sync. Okay, now each of them will have different threshold values to cross. and you will see that as SNR increases, of course, the probability of no synchronization will reduce. Further, if capital H is the number of hops available, then the probability of missing a synchronization between 5 codes is much higher than the probability of, say, missing a synchronization when you have 30 hops. Because if you have 30 hops, you are if you have 30 hops, you are basically frequencies are very finely separated. They are not very broadly separated. They are very finely separated. So even if you lock onto a neighboring signal, even if, like, basically you lock onto a neighboring signal, you will say that you have achieved synchronization because the neighboring signal is not that far away from the actual signal. Whereas when you have 5 hops, provided the bandwidth is same, the separation of signals is too large. So if you have a wrong signal, you will of course not cross the threshold. So you will not get a, you will not miss the detection. So next, yeah, this one is, I think we have covered this one already. Okay, now this is another, which is the active correlator, serial search. So the next technique employs an active correlator for serial search. The first one which we did, match filter bank, that is a example of a parallel search. Now what we will do is serial search. The second technique employs an active correlator for serial search. So if the receiver is in sync with the incoming signal, then all H hops will contribute to the test statistic Z. When Z rises above the threshold level, sync lock is declared. If some of the receiver hop frequencies do not coincide with the incoming hop sequence, then during the periods of no match, the output of the squaring envelope detector will be only noise. So if sufficient number of hops do not match, then Z will not be above the threshold and the control will hold back the clock for one period, thus slipping the code sequence by one chip. That is, there is a test statistic Z. Now, if there is an incoming signal which has a particular hop sequence, so it goes from F5, F4, then F1, then F9, then F2, like that. There is a particular hop sequence. Now you are also generating a hop sequence at your end. So if they are matching, each time they match, because you are multiplying and accumulating, so each time they match, you will have a good amount of contribution to the test statistics, which is basically a square sum. So your test statistics will increase, 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 increase till your test statistic Z crosses a threshold. Then you will say, okay, enough. I have observed enough number of syncs from which I can confidently say that I have achieved sync lock. But if your receiver is not in sync, basically the hop pattern that you are getting and the hop pattern you are generating, they are very far apart. So they are absolutely mismatching. Then each time in each hop, because the hops are mismatching, so the correlation among them will be zero. So the correlator will only give noise. So if you add, no matter, because noise value is so small, no matter how many times you add noise, you will mostly not get to cross the threshold. So you cannot say that you have achieved synchronization. So in this way, because you are only adding noise, so in this way, when there is no hop mismatch, you are only adding noise. Whereas in the parallel search, because we were multiplying with all the hops simultaneously, even in the case of mismatch, we were giving the entire signal power. So there was a, even in case of mismatch, we were passing the entire signal power. So there was more chance of a false alarm. But here, because when there is a mismatch, you only add the noise, and the noise is, no matter how many times you add, it is very unlikely that it will cross the signal threshold. So you can easily say that the probability of false alarm will be much lower. So this is one advantage of serial search. Another advantage of serial search is that it uses very less number of components. But what is the disadvantage of serial search? That it takes a lot of time. Because it is serial search, it is searching all the hop patterns one by one. So if you have a large number of hop patterns, then it is impractical. If you have a large number of hops, if capital H is pretty large, then it is impractical to implement a serial search. Okay, generally declaring synchronization on a single successful attempt will yield poor result and too many false locks. So basically, of course, if you run only once, you are starting from a particular seed value, and you will have, if you, that value may be 100% mismatched to what is coming. So to synchronize the entire code in one run is very tough. So of course you have to do multiple runs. Typically m sequential successful synchronization indications are needed. So here is the synchronization. So what happens is the hop is basically correlated. This is a correlator bank in I and Q domain, correlated and accumulated. So and then this is a comparator which compares whether your signal's test statistic Z has crossed the threshold or not. If it has crossed the threshold, if this one gives 1, then the control will lock the sync, and your pseudo random code sequence generator will only generate that particular hop sequence till it gets further notice from the control to change. So that's why this is threshold comparator will give you the instruction, the controller, to sync lock. So each time basically you give a local code generator. This NCO is the code generator or oscillator, this hop generator. So this frequency hop, each time this frequency hop is generated by this local oscillator, it is correlated with the particular incoming signal, and the result of the correlations are accumulated into and it is passed into a threshold comparator, and when the threshold comparator gives a 1, it locks onto that code till further notice. That is the way of PNC. That is the way of this active serial search synchronization. Okay, the probability of no sync here is basically, again you have to take the probability that you miss a synchronization. So this is the probability of synchronization. So 1 minus the probability of you miss a synchronization, and this one is the probability that you will get a lock onto a particular hop. So that hop probability is this, and this is the probability of no synchronization. So the overall probability of false, okay, yeah. Note that the receiver knows the hop sequence but does not know where the sequence of the incoming signal is located within that sequence. Of course, it knows what sequence, it knows the hop sequence because it locally generates that, but it does not know where and when this hop sequence occurs in the incoming message signal. Okay. Next, a typical hop would be comprised of say 256 frequency. So a search over 256 hop intervals should suffice to find where the sequence is in the pattern. The serial search scheme is slow, but it has a high probability of finding the code sequence. The probability of false alarm is low. So it is slow, but it is reliable. Parallel correlator is expensive and not as reliable, but it is the parallel code is fast. So it is a matter of priorities, whether you want accuracy or you want low latency. So based on that, you will choose one. If you want low latency, you will go with the matched filter, and if you want high reliability, you will go with the serial acquisition. Okay, so this is the probability of no sync for the false alarm probability of 10 to the power minus 4 at various this active correlator or serial search. So if we compare these two graphs, where did the other go? Say at an SNR of 8 dB and you have 5 hops, you see that at 8 dB it is around, if I am not wrong, a 7 into 10 to the power minus 1, that is 0.7. It is at 0.7. So no, sorry, 7 into 10 to the power minus 2, 0.07. So this probability is 0.07. And the same at 8 dB for 5 hops, 8 dB 5 hops. This one is, it is apparently same. Let's check another point. This 6 dB line, if we take, and this 10 hop, we will see it is intersecting exactly at this 10 to the power, I think 9 into 10 to the power minus 3, and it is giving, yeah, so you see this one has I think 3 into 10 to the power minus 2. So 3 into 10 to the power, when you are using matched filter, the no sync probability that you miss synchronizations, that you miss to lock, basically you cannot lock, is 3 into 10 to the power minus 2, much higher than 9 into 10 to the power minus 3. Similarly, at various other points, you may get similar or lower. So when you use active correlator, your probability of false lock or probability of false alarm are, and probability of missynchronization, both are low. Probability of misdetection is also low, and probability of false alarm is also low. But of course, it is slow. Now, next is FHSS synchronization 3. So next is the third correlator, that is called a two-step synchronization. So because of the sporadic characteristics of PTT communication, rapid and accurate techniques are required to facilitate resynchronization. So every time you are transmitting, you will need resynchronization. So the particular mechanism, that is the push to talk mechanism, PTT, that particular push to talk mechanism, you have bursty traffic, you have sequence, then there may be silence, then again there is a sequence. So in the periods of radio silence, the clocks in the transmitter and receiver will go out of sync. So for before every transmission, you have to resynchronize. Now using a low latency serial search here will be not wise, because you are synchronizing before every transmission. So because you are synchronizing before every transmission, you are doing it very often, and serial search is a time expensive process. So doing a time expensive process very often will of course slow down your system. So, and another thing is that of course then you can use matched filter, but matched filter gives a lots of false alarm. So then next, therefore, there is another method, that is the two-level synchronization, which was designed by Theodore Rappaport, the legendary communication engineer. He designed it, which is the two-step FHSS synchronizer. A block diagram of the two-step is shown here. You are comparing two thresholds. One is the matched filter, and another is the parallel correlator, bank of correlators that we have first used. So there is both that parallel search, and then there is a matched. match filter here, and there is the parallel search of bank of active correlator. So you are using one match filter here, and you are using, which is matched to the received signal, and you are using a bank of active correlator to find the exact hop. Okay, the first step is comprised of a passive correlator or match filter, the output of which, if above gamma th1, triggers the second stage, which is a bank of active correlator detector. The bank of active correlator detector we have already done. This is basically a bank of active correlator detector. So this one is what is used in parallel detection. The first one, first FH is a synchronization mechanism. So that is used. And before that there is a matched filter. So if the matched filter response goes above a particular value, only then is the next level triggered. Next, okay, so the two steps. So first there is a match filter. If this match filter output crosses a particular threshold, only then is the second stage, which is the parallel detector, parallel synchronization detector that we have already done, activated. So when match filter exceeds the threshold, it is an indication that a possible sync prefix has been detected. So basically there is a particular small pattern that you have detected. So we can start the synchronization process to synchronize the entire thing. In that case, one of the C active correlators to start to look for the remainder of the hop set. At the end of each hop, if the active correlator has detected enough of the hops, its output will exceed the second threshold, indicating that sync lock has been achieved. So instead of always passing through all the hops, instead of always passing the signal through all the hops, you pass it through a match filter. When the match filter says there is a possibility of synchronization, only then you, to finalize the synchronization, you pass it through a matched filter. You pass it through a bank of active correlator, that is a parallel search. So instead of always doing a parallel search across all the hops simultaneously, you do it only when you have a particular match filter threshold crossing. Okay, if it does not exceed the second threshold, the correlator is made available for subsequent assignment by the match filter. So first the match filter will pre-filter, and then the bank of correlators will finally give you the actual hop sequence. These two will work in tandem. That what happens is you are saving energy by not always using this. Instead, you are using a cheap matched filter to do load the maximum load of the work, and this will only synchronize and if after getting a signal from the matched filter. So that is how you save computational time. The relatively low reliability but fast performance of match filter is used to pre-sort through the possible code offset before time consuming but high reliability active correlator is used. So you use a fast process to basically get a coarse idea about what is there. You get a coarse idea of when synchronization can be done, and after you have got the coarse idea, only then you start the actual reliable but expensive serial searching. Okay. The rationale for such an approach is that passive scheme is fast but hardware intense, whereas the active scheme is slower but hardware light. The effect of interfering signal and jamming tones is essentially to increase the number of false detection in the first step and to increase the load on correlator for the second step. Okay, so basically you if you used only the first step, you will have a load of false detections, and if you only use the second step, you will have a load on the correlators. The hardware will be load overloaded. So this will together be better equipped to handle the incoming sequences. Okay. Yeah. So the false alarm and misdetection probabilities are given like this, and there is a Erlang analysis, load analysis of Erlang B formula. So basically the system is busy, the active correlator is busy. What is the probability of that blocking probability? So what is the probability of that blocking if the coactive correlators are busy? That kind of analysis is given. We'll skip that analysis for now, and we will go to the comparison of mean acquisition times. Figure 3. So this is the active one, means matched filter, and this is the passive one, means bank of correlators. So these are the two methods, the matched filter and the bank of correlator way, to get the acquisition of the PN sequence, hopping sequence for FHSS. So comparison of mean acquisition time. So the active means the serial correlator, the second one which we have learned, whereas passive means the first one we have learned, match filter. So it's clear the passive approach is, as we said, the passive approach, see, it is mostly flat with time. So no matter how many hops it has to sift through, because it is like a matched filter, so it is mostly constant. Whereas because it does not depend on how many hops you have, if you get a particular match, it will lock. It is not searching through the hops one by one. Whereas when you have an active, that is the correlator, bank of correlator approach, then with a bank of correlator you are basically sifting through hops one by one by one. So the acquisition time will increase with hops because you have to sift through all the hops. So as many hops you have, that much amount of time it will take. So in other words, the complexity is big O1 for here and big O(n) for the active one. For the active one it is big O(n), and for passive it is big O1. Okay, so the passive approach is much faster. Of course, O(n) is much faster than O1. Relying on the pre-sorting possible with the mesh filter significantly shortens the code acquisition time. Okay, so these times are short enough to facilitate PTT communication. So if you take the two-step, okay. Now, just as for DSSS, after course acquisition establishes the code synchronization to within a single time or code symbol, handoff to the tracking mode occurs. So basically, you have done a course adjustment with the FHSS acquisition. Now you have to do FHSS tracking. FHSS tracking will ensure that your code is in lockstep with the your locally generated code is in lockstep with the received code. So one is to get the broad idea of which code is being transmitted, and the second one is to make sure there it is in lockstep with the code that is actually being sent. Okay, so now for tracking, just as for DS3, after course acquisition, it will hand off to tracking. The tracking maintains the code synchronization within small fraction of a single chip. So it will allow the it will not allow the synchronization gap to exceed more than one chip time, because if it exceeds more than one chip time, it will go out of sync. So that is the goal of FHSS tracking. Okay, just give me 2 minutes break. I will come back in 2 minutes. এখন থেকেই তোমায় করতে হবে। কোর্স ওয়ার্ক কি আছে, তুমি আগে 5টা সাবজেক্ট করতে, এখন তো একটা নাকি দুটো সাবজেক্ট। ল্যাব থাকলে অনেক টাইম লাগে, ল্যাব রিপোর্ট লিখতেই সারাদিন চলে যায়। এমটেকের সময় তো আমি যত না পড়েছি তার চেয়ে অনেক বেশি ল্যাব রিপোর্ট লিখেছি, সারাদিন খালি ল্যাব রিপোর্টই লিখতাম। Okay, so now we come to FHSS tracking. So in FHSS tracking, again we have the early late tracking like we have in DS3 tracking. In DS3 tracking, you can see there is an early late tracking that we have discussed. Just for revision, I will go back. So in early late tracking, you pass the code through a early generator, early flip flop, then you pass through a middle flip flop, then you pass through a late flip flop. Now you do a XOR of the early flip flop, you do a XOR of the late flip flop, and you accumulate those XOR values, and finally you will get a you do a subtraction of the correlation of the early and late, and you will get a particular point where it will cross zero. You will get an intermediate zero crossing point. This, if this zero crossing point is in the middle of the entire time span, then your uh, codes are in sync. If not, they are out of sync by the amount of time which the in sync point has shifted from its actual balance point or center of gravity. So that is the principle of early late tracking. So here also in FHSS we implement some sort of early late tracking. Yeah, so there is a early generator and a late generator, and of course there is a VCO, because here the things are done in frequency, not in time. So there is a VCO which controls the early generator oscillator, and there is a VCO which controls the late generating oscillator, and this oscillator early generating frequency and the late generating frequency both are combined with the received signal, and they are pass through a band pass filter and an integrator to basically get the correlation value. So yeah, if the receiver is early, that is the gate occurred too early compared to chip, then at the end of the chip duration there is a negative value. So if it is early, if the code is early, then see, if there is a if the code is early, the early gate will give a negative value, and if the code is too late, then at the end of the chip there is a remaining positive value out of the comparator, as shown in figure 1D. So if you see, you are passing this through a comparator. G1 is the output for the early, G2 is the output for the late, and then you are passing them through this comparator. So if there is a negative tail, then it is early. If there is a positive tail like this, then it is late. So if the receiver is early, then at the end of the chip duration there is a negative value out of the comparator, indicating that to the voltage control clock to shift later in time, because it will give a negative value. That negative value is again fed to the VCO, and that VCO will of course then shift the frequency in one direction. And finally, if the receiver is too late, then at the end of the chip there is remaining positive value, indicating the clock to adjust the time so that the early and late gates occur earlier. Okay. There is always some residual phase jitter in the early late tracking due to uncertainty in clock matching. The variance of the jitter is given. Jitter means the variability in the sequence tracking. So you say that, like, you are expecting the standard sequence clocks to have a particular timing, but they may be out of sync themselves. That will create a slight amount, that will create a slight jitter. So the variance of that jitter is given here. So this is the early late acquisition tracking problem. Now, of course, there is a, again we have to do a misdetection and false alarm analysis. So the misdetection is given by this, and the false alarm is given by this, where the Q function is basically the integration of Gaussian. And this yeah, gamma dash is basically the SNR threshold, where you decide whether detection has happened or not, locking has happened or tracking has happened or not. Okay, the probability of miss in tracking loop is given by this. There are a wide variety of control processes. Recall that one of the goal of tracking is to return the course synchronization as quickly as possible when that function has incorrectly established what it thought was synchronization. So basically, if you achieve synchronization and then you see that okay, synchronization was actually wrong, we did a false alarm, then it has to again, as soon as possible, code go back to the code go back to the course tracking. So that is there. Now yeah, SNR of 5 for the so these analysis, these are basically same Raysian fading analysis. So the rest of the tracking analysis is for FHSS is same as DS3. So this is the mean time, mean acquisition time, and then there is the Raysian fading model, like that. Okay, now I will briefly touch upon linked budget. So linked budget means the amount of power that you have to keep as margin. So you are transmitting certain power, it is being boosted by the antenna. Then there might be some device losses. So throughout from the point you have transmitted the power to the point you have received it, constantly there is addition and subtraction to that power, and the power that you finally receive is very different from the power that you have transmitted. Now, a receiver has something called a sensitivity, receiver sensitivity. So, if the power level it receives finally after all the addition and subtractions, if the power it receives finally is lower than that particular dB of sensitivity, then it basically detects noise. So each receiver has something called a signal or noise detection, a Neyman Pearson detector. That Neyman Pearson detector has a particular threshold. If it crosses that threshold, then it is a signal. If it does not cross that threshold, it is a noise. So we have to budget our power. We have to send our power at the transmitter in such a way that we account for all those losses, and after that also we will be at least a few dBs above the receiver sensitivity, because the receiver sensitivity is the absolute bare minimum that power must reach the receiver. So you have to maintain a margin above that receiver sensitivity finally to, and you have to calculate your transmit power as such. That is called link margin. So that power say you are 10 dB, your receiver sensitivity is minus 90 dB. That means any power that is lower than minus 90 is considered to be noise, not signal. No matter what the content of the signal is, it will be considered to be noise. So because the threshold is minus 90, so that means if you are transmitting power at say 0 dB and you finally get different kinds of loss, and finally you have minus 60 or minus 70, say minus 70, finally the receiver gets, you are transmitting 0 dB and all the deductions finally gives you minus 70 dB. That means your link, what is your margin now? Your margin is 20 dB, because it can only go 20 dB below. It is minus 70, it can only go 20 dB below to minus 90, after which it will not work. So your link margin is 20 dB. Okay. So now in this link margin, see, first the power is getting transmitted, it will have some implementation loss at the transmitter. Each device within this transmitter blockchain will have some inherent loss of its own. So these losses will get added up and you will finally get some combined loss, say 1 dB, 2 dB, 3 dB from the transmitted. Then there will be something of an addition, which is the antenna gain. So PTX, you have, yeah, let me take the pencil very quick. So you have PTX. What is the power you are receiving? You have to send PTX. Now from PTX, a LT will get subtracted as the implementation loss of the transmitter. Now from there, these are all in dBs. Okay, there will be a GT, power gain, because of the antenna. Now you will have free space path loss, LFS. What is free space path loss? Free space path loss is given as free lambda by 4 pi t whole square. This is your free space path loss. There is G1, G2, but G1, G2 here we are considering separately antenna gains. So we are considering only the strict free space path loss, that is after leaving the antenna. So that is lambda by 4 pi d whole square, where d is the antenna aperture and lambda is the wavelength of the radio signal. So you will have a lambda by 4 pi d whole square loss. That is your free space path loss, LFS. LFS is equal to, because it is in dB as I said, 10 log 10 lambda by 4 pi d whole square. The 10 log 10 of this. Now, then there will be fading. Why fading? Because of the multipath. And then there will be interference. So you don't know how much fading and how much interference will happen. That is not in your hand. When you are designing the receiver, you don't know how many other receivers will be there, right? That is absolutely not in your hand. But you can budget for a maximum. You can say that under practical scenarios, the maximum interference that it will suffer is 5 dB. So you keep an interference margin of 5 dB. So 5 dB will be reduced from the transmitted power. Similarly, because of multipath, there will be fading. That fading, you say for a particular environment, say urban environment, you will have only 5 dB fading. So you keep 5 dB margin for fading. Now, once you have that, then of course there will be a boost because of the antenna gain. Then there will be a noise. You have to remove that noise. And then there will be a implementation loss at the receiver. Now all this addition is only because of antenna gain and various subtractions together must be, now this power must be something above the link margin, right? So the link margin say is M. M is the link margin. So this power, the effective power that you are receiving, should be something less than N, something greater than N. So that thing minus N is basically your receiver sensitivity, right? Receiver sensitivity means if you subtract from the effective power, if you from the final received effective power, it should be above some dBs above the receiver sensitivity. Or you can write like this. Actually, this one will be more logical. Now from all this is the effective receiver power. Now this effective receiver power has to be somewhat above the receiver sensitivity. This is the Rx sensitivity. It has to be somewhat above Rx sensitivity. So the how much margin it is above Rx sensitivity, that is your link margin. So this is the theory of link margin. Now of course there is problems based on link margin which you have got in your assignment. These are pretty straightforward problems. You just have to do addition, subtraction. So you have 10 dBm transmit power. There is a 0 dBi gain. So you still have 10 dBm. Now there is a path loss of 88 dB. So you subtract and you get minus 78 dBm. There is a gain of 0 dB. So you still have at the antenna. So minus 78 dB. So you receive minus 78 dB. Now there is a noise minus 81 dB. Now the noise figure is plus 10 dB. So the effective noise is minus 71 dB. So the implementation loss at the receiver is 4 dB. So the SNR of the receiver, signal to noise, signal minus noise in dBs basically. So signal is minus 78, and from there 4 will be also further subtracted. So minus 82. Minus 82 minus of minus 71. So you have minus 11 dB SNR, and required SNR is 9.6 dB for communication. So you have your required SNR, you are way below required SNR. So you have a deficit of minus 20.6. You take another example. Here you have 10 dBm. There is a gain of 12 dB at the antenna. So you have 22 dBm. Now the path loss is minus 88. So you have minus 66 dBm. Then there is a 12 dB gain at the antenna receiver. You have minus 54 dBm signal. So your minus 54 is your receive signal. Now this receive signal will suffer an implementation loss. So you will have finally minus 58. And your thermal noise is minus 81. And your noise figure is plus 10. So noise figure means how much noise the hardware itself can handle. So this one will be minus 71 dBm. So this minus 71 dBm minus 58, you have to subtract minus 71 from minus 58 and you get plus 13 dB. And the required SNR to get 10 to the power minus 5 BER is 9.6. But your SNR at the receiver is 13 dB. So you are 3.4 dBs above the link margin. So communication is possible. But here communication is not possible. So that is the concept of link margin. Thank you. That will be all for today. See you next week.